Hello everyone, welcome back to the Atharva Gate Academy. Myself Chinmay Dhaduk. In this video, we will continue to solve previous year GATE questions of Strength of Materials of Chapter 2. Here this first question is from year 2016, paper set 2. A circular metallic rod of length 250 mm is placed between two rigid immovable walls as shown in the figure. The rod is in perfect contact with the wall on left side and there is a gap of 0.2 mm between the rod and the wall on the right side. Means here there is no gap between this wall and this end, and here there is gap of 0.2 mm between this rod and this wall. Fine. If the temperature of the rod is increased by 200 degrees Celsius, the axial stress developed in the rod is blank, and we have to find this stress in megapascal. Here value of Young's modulus is given, that is 200 gigapascal, and coefficient of thermal expansion is given, that is 10⁻⁵. Now here it is given that change in temperature is 200 degrees Celsius, means delta T is 200 degrees Celsius. Here we are increasing the temperature, so length of this rod is going to be increased, right? Here we can get two cases. In first case, this change in length may be less than 0.2 mm, right? And in second case, we can get this change in length is greater than 0.2 mm. And here this is the gap having value 0.2 mm. Let's say this gap is lambda. Understand that if change in length by increasing temperature delta T is less than 0.2 mm, then this end of rod will not touch this wall, right? And we can understand that this case will be case of free expansion, right? Because in first case there will be no restriction to change in length, and we know that if there is no restriction to change in length, the value of stress is 0. Fine. So first of all we will find change in length delta L. We know the equation to find out change in length. It is L alpha delta T. Here L is initial length, that is 250 mm. So it is 250 into alpha is 10⁻⁵ into delta T is 200. Here this length is in mm, so this change in length is also will be in mm. And if you will calculate this, then you will get 0.5 mm, right? Here this 0.5 mm is greater than 0.2, means here delta L is greater than 0.2, means it is not the case of free expansion. So here value of sigma is not 0. Now we know that how to find thermal stress in partially restricted body, right? First of all we will assume that this wall is not there, means there is no restriction to change in length of this rod. So if we increase 200 temperature of this rod, then this rod is going to be deformed and length of this rod will increase like this, right? And we know that this change in length is 0.5 mm, right? Now we know that here there is wall at distance of 0.2 mm from this end. So now we will compress this rod by a reaction, let's say R, up to this wall, or we can say up to this point, right? So final deformation in this rod will be 0.2. So here by this reaction we are deforming this rod up to this point, or we can say up to this surface, and here this deformation is, let's say, delta R. Fine. Now we know that value of delta R is RL by AE, right? Actually this reaction is compressive reaction, but here we are taking only magnitude, so here we will take this R as positive. Now from this figure we can understand that this delta R plus this gap, that is 0.2, will be equal to this total change in length, that is 0.5, right? So we can write that 0.5 mm is equal to 0.2 plus delta R. I hope that you understand this. Actually this value of deformation should be negative, right? Because here by this reaction dimension of this rod is decreasing, but we are only taking magnitude here. So from here we can say that delta R is equal to 0.3 mm, right, and delta R is equal to RL by AE. Here R divided by A will be stress, so it is stress into L divided by E. This R divided by A is load divided by area, that is stress, right? So now from here we can say that sigma is equal to 0.3 into E divided by L. Now we have the value of E, that is 200 gigapascal. So we will convert this value of E in megapascal. So it will be 200 into 10 raised to 3 megapascal. And length is given as 250 mm, right? So it will be 250 mm. Now if you will put this value E and L in this expression, then you will get value of stress. And this value of stress will be stress in this rod, right? Finally, if you will calculate this stress, then it will be 240 megapascal. Here, unit of this 0.3 is mm, unit of this length is also mm, and unit of this E is megapascal. So finally, we will get this stress in megapascal, right? And here we have to answer that it is 240. So I hope that you understand this question. This question is for 2 marks. Next question from year 2016 paper set 3 is engineering strain of a mild steel sample is recorded as 0.1%. The true strain is dash. Here it is given engineering strain and it is given in percentage. So from here our engineering strain will be 0.1 divided by 100. So it will be 0.001. And here we have to find out value of true strain, epsilon t. We know the equation to find out true strain, that is ln into bracket 1 plus epsilon. And here this epsilon is the value of engineering strain, right? So it will be ln into bracket 1 plus 0.001. Now if you will calculate this value, then you will get true strain. But in the options, all the values are given in percentage. So finally you have to multiply this value with 100 and then you will get this value. So in this question answer will be true strain is equal to 0.099%. Fine, and this question is for 1 mark. Next question is from year 2016 paper set 3. A square plate of dimension L cross L is subjected to a uniform pressure load P is equal to 250 megapascal and it is acting on its edges as shown in the figure. Here you can see this square plate and this pressure is acting on the 4 sides of this plate. Assume plane stress condition. What is the meaning of plane stress condition? It means that this plate is having stress in only 2 directions. One will be in this direction, let's say this direction is x direction, and second will be in this direction, that is y direction. In z direction value of stress will be 0, means this condition is called as plane stress conditions. Fine. And here Young's modulus E is 200 gigapascal. The deformed shape is square of dimension L minus 2 delta, that is shown here. This dotted line is deformed shape. If L is equal to 2 meter and delta is equal to 0.001 meter, the Poisson's ratio of the plate material is dash. Means here we have to find out mu. Now here we can understand that due to this pressure there will be stress in this plate, right? And here we can say that stress in x direction will be minus p, right? That is shown here, and stress in y direction is also minus p. This pressure is compressive, so here we will take minus p. Fine. And here value of sigma z will be 0, right? Because it is plane stress condition. Now remember that we have discussed this equation in the chapter 2 and topic is volumetric strain for triaxial load, right? Here you can see that this epsilon x means engineering strain in x direction is equal to dl by L, means change in dimension in x direction divided by original dimension in x direction, which is equal to sigma x divided by E minus mu sigma y divided by E minus mu sigma z divided by E. Fine. Now in this example we will use this equation to find out Poisson's ratio mu. In this case value of sigma x, sigma y and sigma z is known. Here sigma z is 0, so this term will be 0. So we will have these two terms. dl by L is equal to sigma x by E minus mu sigma y by E. Here this dl is change in dimension in x direction. Here we have taken this direction as x direction and we can see that this distance is delta, right? So here this distance is also delta. So total change in dimension in x direction will be 2 delta, right? And this dimension is decreasing, so we have to take this dl is equal to minus 2 delta, right? So here we can write minus 2 delta divided by capital L. Here initial length in x direction is capital L, fine, and it is equal to sigma x, that is minus p, divided by E minus mu into sigma y, that is also minus p, divided by E. Now here we will take this minus sign common from all the terms, so it will be plus, plus and plus, right? Here value of delta and L is given in unit meter, so it will be 2 into 0.001 divided by length is 2 meter is equal to P divided by E into bracket 1 minus mu, right? Now here we have value of P in megapascal, so we have to take this Young modulus in megapascal. So this value will be 200 into 10 raised to 3 megapascal, right? And now we have to put these values here. So finally we will get value of mu, fine. If you calculate this value, then you will get mu is equal to 0.2, and here you have to write 0.2. That is the answer of Poisson's ratio of plate material, fine. And this question is for 2 marks. Now see, here you may think that we can apply this equation mu is equal to minus lateral strain divided by linear strain, right? But it is for axial loading condition. It is not for 2D loading condition or 3D loading condition, fine. Now the next question is from year 2017 paper set 1, and this question is from chapter 1. A point mass of 100 kg is dropped onto a massless elastic bar having cross-sectional area 100 mm square and length is equal to 1 meter, and Young's modulus is 100 gigapascal. Mass is dropped from height h, that is 10 mm, as shown in this figure. If g is equal to 10 meter per second square, the maximum compression of the elastic bar is dash. Means here we have to find out maximum value of deformation in this bar. Now we know that delta is equal to PL by AE. Here we have length, area and Young modulus of this bar, and here this P is axial load acting on this bar, right? But in the chapter 1 we have discussed that if we drop any mass from any height, then load by this mass will be impact load. It will be impact load. So in this case, load by this mass of 100 kg on this bar will be impact load, and we know the equation to find out impact factor for this case. We have discussed this equation of impact factor in chapter 1. It is equal to 1 plus under root 1 plus 2 into h divided by delta static. Here h is this height and this delta static is PL by AE. And to find this delta static, we will take load by this mass as static load. Means here we will take this mass is equal to m into g. Fine. So from here, if you will find delta static, then it will be mass into g, that is 100 into g is 10 into length is 1 meter. Here we will take 1000 mm divided by area is given as 100 mm square. So it will be 100 into Young's modulus is 100 gigapascal. Here we will take Young's modulus in megapascal. So it will be 100 into 10 raised to 3 power. Fine. So from here value of delta will be 0.1 mm. Now we know that delta impact is equal to impact factor into delta static. Here we have value of delta static. Now we have to find out impact factor from this equation. In this equation we have value of delta static, that is 0.1 mm, and we have value of height, that is 10 mm. So here we have to put h is equal to 10 mm and this delta static is equal to 0.1 mm. So from this equation you will get value of impact factor, and if you will multiply this impact factor with value of delta static, that is 0.1 mm, then finally you will get deformation due to impact load, and that will be the maximum value of compression of this elastic bar. And here if you will take this deformation in mm, then finally you will get value in mm. And here this value is 1.5177. You can calculate this and get this value. Fine. And here we have to write 1.5177. It is asked in mm. Fine. And this question is for 2 marks. So from here we have to understand that load by this mass will be impact load. So here we have to multiply this deformation by impact factor. Fine. Next question is from year 2017 paper set 1. In the engineering stress strain curve of mild steel, the ultimate tensile strength UTS refers to yield stress, maximum stress, proportional limit, or fracture stress. We know that for mild steel, engineering stress strain curve is like this, right? And here we have ultimate tensile strength, and this point is ultimate point. Value of stress at this point is known as ultimate stress, and it is actually ultimate tensile strength, right? That we have discussed in the theory part. From this curve we can say that this point shows the maximum value of stress that this mild steel can withstand. Fine. This next question is from year 2017 paper set 1. A horizontal bar fixed at one end, x is equal to 0, has a length of 1 meter. Means here let's say we have this fixed end and we have bar like this. Here we have to take this point as origin point, because at fixed end value of x is 0, means at this point value of x is 0. It is having length of 1 meter. Let's say here this length is capital L and L is equal to 1 meter. And 1 meter means it is 1000 mm, right? The cross-sectional area of 100 mm square, means capital A is 100 mm square. Its elastic modulus varies along its length as given by E of x is equal to 100 into e raised to minus x gigapascal. Means here Young's modulus is the function of x, means it is the function of length of this bar. Fine. Where x is the length coordinate in meter along the axis of the bar. Fine. The axial tensile load of 10 kN is applied at the free end, where x is equal to 1. Means here we know that x is equal to L and it is 1. So at this point we apply tensile force like this, and it is having value 10 kN, so it is 10 raised to 4 Newton, right? Here we have to find out the axial displacement of the free end. Means we have to find out deformation at x is equal to L. Now here value of E is not constant, so we have to use equation of delta, that is equal to integration from 0 to L P as a function of x into dx divided by A as a function of x and E as a function of x. Fine. Now here value of load and area is constant, so delta is equal to P divided by A integration 0 to L dx divided by Ex, and here this Ex is given as 100 into e raised to minus x. So it is 100 into e raised to minus x. Now here this 100 is constant. So we can say that delta is equal to t divided by 100a and integration from 0 to L. And here if we take this e raised to minus x in numerator, then it will be e raised to x into dx, right? So it will be P, that is given as 100 kilonewton, means it is 10 raised to 4 Newton, divided by 100 into area. So it is 100 into area is 100 mm square. So it is 100 mm square. And integration of e raised to x is e raised to x. So it will be e raised to x from 0 to L. Here this 10 raised to 4 and this 100 is cancelled. So finally we have e raised to L minus e raised to 0, right? That is value of this term. Now here it is given that this length coordinate in meter. So here we have to take this length in meter. So it will be e raised to 1, because here this length is 1 meter, minus e raised to 0 is 1, right? So it is e minus 1. So if you will calculate this value, then you will get 1.718. Fine. And this answer will be in mm. Now understand that why this unit is in mm. Here in this equation we have taken this load in Newton. This length we have taken in meter, right? Here we have put this length in meter. So it is Newton into meter divided by this area is in mm square, right? Here we have taken this area in mm square, and E is taken in gigapascal. So it is in gigapascal. Now here if you will convert this meter in mm, then we have to multiply this value with 10 raised to 3. So finally it will be Newton into mm divided by this area is in mm square. And if you will convert this gigapascal value in megapascal, then you have to multiply denominator with 10 raised to 3, right? So finally it will be megapascal. And here this 10 raised to 3 is cancelled. And we know that this megapascal is nothing but the Newton per mm square. So here if you will simplify this, then finally you will get mm, right? So here this answer is in millimeter. I hope that you understand it. This question is for 2 marks. In this question you can get variation in Young's modulus, or you can also get variation in area. But you have to remember this equation. By using this equation, you can easily find the value of deformation in any bar. Fine? Next question is from year 2017, paper set 2. A steel bar is held by 2 fixed supports as shown in the figure, and it is subjected to an increase of temperature delta T 100 degrees Celsius if the coefficient of thermal expansion and Young's modulus are 11 into 10 raised to minus 6 per degree centigrade and 200 gigapascal respectively. The magnitude of thermal stress in megapascal induced in the bar is dash. Means here we have to find out thermal stress sigma T. And we have discussed these questions I think 2 times. We know the equation to find out thermal stress in this case, where we have one bar which is fixed at both the ends. It is E alpha delta T, right? Here we have value of E, alpha and delta T, that is given in the question. Here we have to take this Young's modulus in megapascal, alpha in per degree centigrade and this delta T in degree centigrade. So finally you will get value of thermal stress in megapascal. And here our answer will be option A, 220 megapascal. Fine. This question is for 1 mark. Next question is from year 2017, paper set 2. A rod of length 20 mm is stretched to make a rod of length 40 mm. Means initial length is 20 mm and after stretching length is 40 mm. Subsequently, it is compressed to make a rod of final length 10 mm. Means we are compressing this rod and final length of the rod is 10 mm. Consider the longitudinal tensile strain as positive and compressive strain as negative. The total true longitudinal strain in the rod is dash. Means here we have to find out true strain. Now we know the equation to find out true strain, that is ln into bracket 1 plus epsilon, and here this epsilon is engineering strain, that is delta L divided by L, means it is final length minus initial length divided by initial length, right? Here this length is initial length. Now see, here value of engineering strain does not depend the value of intermediate length. It only depends on final length and initial length. Here we have value of final length and initial length. So here we don't have to use this value. So our answer will be 10 minus initial length is 20 divided by initial length 20. So finally this will be minus 0.5. Now we have value of engineering strain, and now we will put this value in this equation. So it will be ln into bracket 1 minus 0.5. So finally it will be ln 0.5. And if you will calculate ln 0.5, then it is option B minus 0.69. So our answer is option B. And this simple question is for 2 marks. So I hope that you understand. Here it only matters the final length and initial length. We don't have to consider the intermediate length. Fine. Next question is from year 2018, paper set 1. In a linearly hardening plastic material, the true stress beyond initial yielding increases linearly with the true strain, decreases linearly with the true strain, first increases linearly and then decreases linearly with the true strain, or remains constant. Here you have to remember the stress strain curve for linearly hardening plastic material. It is inclined line like this, and then it is like this. From this diagram you can see that this is the initial yielding of this material, right? And beyond the initial yielding you can see that true stress increases linearly with the true strain, right? So here our answer will be option A. Here you have to remember this diagram. This question is for 1 mark. Next question from year 2018, paper set 1 is a bar is compressed to half of its original length. The magnitude of true strain produced in the deformed bar is blank. We have discussed this same question in previous video, but in that question here there was value instead of magnitude, right? Let's say initial length is L, then final length will be L by 2, because this bar is compressed to half of its original length. So in this case value of true strain will be final length minus initial length divided by initial length, right? It is delta L by L. So it will be L by 2 minus L divided by L. So finally it will be minus 0.5. This is the value of engineering strain. Here we have to find out true strain. True strain is equal to ln into bracket 1 plus epsilon. So if you will put this value here, then you will get ln 0.5 and it is minus 0.69, right? Now in previous video we have written the answer minus 0.69 because in that question we have to answer the value of true strain. But in this question we have to write the magnitude of true strain, and I have told you that whenever magnitude word is mentioned in the question, then we have to write this value positive. Means here we have to write 0.69. We don't have to write negative sign in this answer. Fine. So here our answer is 0.69 and we have to write answer up to 2 decimal place. So this simple question is for 2 marks. Next question is from year 2018, paper set 2. A bimetallic cylindrical bar of cross-sectional area 1 meter square is made by bonding steel having Young's modulus 210 gigapascal and aluminium is having Young's modulus 70 gigapascal. and aluminium having Young's modulus 70 gigapascal as shown in the figure. Here you can see this arrangement. Fine. To maintain tensile axial strain of magnitude 10 raised to minus 6 in steel bar and compressive axial strain of magnitude 10 raised to minus 6 in aluminium bar, the magnitude of the required force P in kilonewton along the indicated direction is dash. Means here we have to find out this value of load. Here given values are A is equal to 1 meter square, Young's modulus for steel is equal to 210 gigapascal, Young's modulus for aluminium is 70 gigapascal. This strain is also given. Value of strain for steel bar is 10 raised to minus 6. And it is given that it is tensile axial strain, means it is positive. And strain for aluminium is negative because here it is given that it is compressive axial strain. So it will be minus 10 raised to minus 6. Fine. Now here we know that if we apply load in this direction, then there will be reactions on both this end. Let's say this end is end A and this end is end B. So here we will take reactions in opposite direction like this. Let's say this reaction is RA and this reaction is RB. Now see, here you can take these directions of reaction in any direction. You can also take this reaction in this direction. If you will take this direction, then finally you will get RA is equal to negative value. Means you have taken opposite direction. So finally you have to take opposite direction, right? But right now we are taking this direction in left direction. Fine. And let's say here this surface is C. Here length of both the bars is given as L by 2, L by 2. Now we know that deformation between point A and point B will be 0. Delta between AB is 0. And here this delta AB is nothing but the change in length between AB. Now we can say that delta AB is equal to delta AC plus delta CB, right? Here this delta AB is summation of these both deformation because these both bars are in series, right? Now we know that delta is equal to PL by AE. Now here we will write PL by AE for AC plus PL by AE for BC. Here this AC means it is for steel bar and this BC means it is for aluminium bar. Now here we have length is L by 2 for both the bars. We have area that is same for both the bars, but value of E is different for this both bar and value of load P will be different. Here we have to find this load in AC bar and this load in BC bar. To find out load in AC bar, we will take section in bar AC like this and we will take summation of all the forces acting on this bar either side of this section. Here we will take left side of the forces. So it will be RA. So it is RA into this length is L by 2 divided by area and Young's modulus is 210 gigapascal. Plus to find out load in BC member, we will take section in part BC and we will take summation of forces either side of this section. Now in this case we have taken left side of the force, so in this case we will also take summation of left side of the forces. So it will be RA minus P, right? Here it is acting away from the section and it is acting towards this section. So it will be RA minus P. Here the length is L by 2 divided by area and Young's modulus is 70 gigapascal. And it is equal to 0. Now here we can take L by 2 common and area common and it will be multiplied with 0, so finally it will be 0. So we can write from here that RA divided by 210 plus Ra minus P divided by 70 is equal to 0. And from this equation we can find out value of reaction at end A. And it will be 3P by 4. You will get this reaction in terms of load P. Fine. So we have this one equation. Now see, here we have strain in steel bar, that is given as epsilon s is equal to 10 raised to minus 6. And we know that this engineering strain is equal to change in length divided by initial length, right? Here change in length is nothing but the deformation in this steel bar, and that is given here. This is the deformation in steel bar, right? And it is having value this term. It is delta in steel bar, means it is delta L for steel bar, right? So from here we can say that delta L is equal to Ra into L by 2, Ra into L by 2 divided by this area into 210, and it is in gigapascal, so into 10 raised to 3 will be megapascal, right? This is value of Young modulus in megapascal. And divided by initial length, that is L by 2, right? So from here this L by 2 is cancelled, and area is given as 1 meter square. So here we have to put this area in mm square. So it will be 10 raised to 6 mm square. So you have to put 10 raised to 6 instead of area. And from this expression you can find out value of Ra, right? And if you have value of Ra, then from this expression you can find out value of P. And here this value of Ra will be in Newton. And finally you have to put value of load in kilonewton, right? If you will calculate this, then you will get value of load, that will be 280 kilonewton. And here our answer will be option D, 280 kilonewton, right? I hope that you understand this question. It is little bit lengthy and difficult, but it is also for 2 marks. Fine. Now here chapter 2 is completed, and I hope that you understand all the questions from chapter 2. If you have any doubt, then you can tell me in the comment box, and if you like this video, then make sure that you hit the like button. Also share these videos with your friends and classmates so that they can also take benefit from this channel. Now today we will stop here and we will continue in the next video. Till then, stay motivated and happy practicing.